Okay, hi guys. So I had some trouble setting this up. Apparently, I'm too old for this. But yeah, I had to check a couple of things, and then I think it should be good to go now. Um, okay, so like I said, I'm basically going to be showing you guys some tricks on some basics of complex numbers. That's what I'm going to be doing today. It's one of those topics that every math student faces sometime or the other because it's a very tricky topic. Apart from it being tricky, it's also bulky. So what I hope to achieve here is just a couple of tricks and basics to figure out about complex numbers that you could learn in under an hour. And if you have like a test or an exam, might be really important for you. Okay, and to help today, I just got a PDF, basically like a source online, and I mean it's publicly available. You guys can check this out if you want. I really just searched up and found something, just as a guide, and we could go through it together. Um, but yeah, this is what is included in the slides. It's from University of Surrey. Like I said, everything is all here. You guys can, if you need a link, you can just ask me for it. But it's right there. And oh, by the way, my name is Kingsley. Or if I didn't mention that, I'm so sorry for that. My name is Kingsley. I'm an engineering student, and I've always had an interest in math, and just try to help others get more familiar with it. So, without basically further talking, we could just go straight up to the topic. Here's my pen. Okay. All right. So, complex numbers. Now, like I said, it's something very tricky that people has always had issues with. But really, it all boils down to your set of numbers, and that's probably one of the first topics you would learn in an A level maths. Your set of numbers, and in your set of numbers, what you should have would be the first one would be your set of integers, right? I think this is too big. Let me just reduce it. Pen, okay. So you should have your set of integers, and in here you would have basically one, two, three, four. This is positive, and then if you wanted like the negative integers, you could get the opposites, right? Minus three, and then dot 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 here, minus two, minus one. Okay, so you have your integers. You have your set of integers. You should also have your set of natural numbers, which you guys should know that as well. It's just one, two, three, four, five. You have your set of rational numbers, basically one integer divided by the second integer. You have your set of real numbers, right? Real numbers are numbers that you could actually visualize in a real number line, you know. And this is your number line, by the way. If you have zero and you have minus one this way, and you have plus one plus 2 this way, and in here you could have 1.5. Basically any number you could find, you could visualize on this, falls into your real number category, right? So now the set of complex numbers or imaginary numbers is basically related to these real numbers, and where it comes from is the fact that this particular number cannot be solved. This root minus 1. So root minus 1 is that special number that can't be solved. With a calculator, with like any math system or tool you could think of, it basically can't solve this because it doesn't fall under the real number range or the real number set, you know. Basically your calculator should give you any real number, you could get it from your calculator, right? If it's pi times 2, pi plus 2, anything you could think of, your calculator should bring that out for you, except one number. root minus 1. So then that's where it came about, it being an imaginary number, since it's technically not a real number, but it's used for various reasons. So that's why it's called an imaginary number. Imaginary number. So you could just remember that imaginary numbers are, I mean, they are not real numbers. There are lots of applications for it. That's why we can't like ignore them. But that's basically why they're called imaginary, because there's no actual value for it. It's just like I would say a made up concept, but of course it's not completely made up. Anyways, that's what we have as imaginary number. And like I said, that's the basic root minus 1. And then um that means using our knowledge of swords, any kind of imaginary number, like we could bring more complex numbers from this or more imaginary numbers from this. Because how we could do that is, your so we said root minus 1 is where it starts from, right? But what if you were given root minus 4, right? If you're given root minus 4, what's the relation with this and this? Now, remember from your swords, when you have a root, if you have roots A, B, it's basically the same thing as root A times root B. So basically, just whenever you have a negative number in the square root, take the negative number outside, take the other number, and then solve it. So this would be root minus 1 times root 4. And you know what root 4 is, right? It will be 2 root minus 1. And you can do this for various other like numbers. It's limitless really. Even if this is not like an actual perfect square, if it's like root minus 5, for example, we have root minus 5, it's still the same thing, root minus 1 times root 5, right? And now that basically just easily shows you that any number you have that's an imaginary number, it doesn't have to be just minus 1 here. Like whatever you have here, you could always simplify it to a product of root minus 1 and anything else. And then since it's an imaginary number, we've said that it's imaginary. It's a made up concept really. And so for the purpose of complex numbers, right? For the purpose of this topic, whenever you see root minus 1 or whenever you have root minus 1, just replace that with a j. And now, depending on where you are, it might be a j or it might be an I. If you're listening from Nigeria or watching from Nigeria, you most likely are using an I. If you're watching from somewhere aside from that, it might be a J. They really just mean the same thing. Remember, it's completely made up. It's just a way for us to describe what the number is, right? So yeah, anywhere you see a root minus 1, just think of it as I, think of it as J, which means in this video, I'll probably just stick with I. So which means this is the same thing as 2I, and this is the same thing as root 5I, or I personally like keeping the I behind the number if it's a root. Okay, I root 5. So you've seen easily that any kind of questions we get on this, you can just, it's really not hard to do at all. Let me give you something else random. You could try this out yourself. If you have root minus 36, it's basically the same thing as root minus 1 times root 36, which should give you, remember, anywhere you see root minus 1, replace it with an I. And you root 36, we know that as 6. That's 6I. And that's what where you get. So remember, it always works, always works. No matter what is inside the sword, just take it out, and using your knowledge of sword, you can just handle the complex or the imaginary part, and then figure out the real part. So down to its basics, that's really what imaginary numbers are about: a product of root minus one, some kind of playing around with that. So they shouldn't scare you that much when you know that that's what the basic is really. And so now that we've talked about what the basic is, we've talked about what I is as root minus one, we could now try to define a complex number, right? And remember from this, almost all sets in maths have defined. There's an actual definition to it, right? Where just by looking at the number, you can know with the definition or with the formula what set that number fits in. Complex number also has that as well. And for the sake of complex number, the definition is, let me just go to a different page here. So for a complex number, a complex number is basically a number that has you could say x plus y j down to its bones. This is what a complex number is made up of. It has a real part and it has an imaginary part. And remember again why it's called imaginary, root minus one, right? So this is the real part, this is the imaginary part. So if you got a question saying something like 5 plus 3i, what is the real part of this complex number? The real part would be 5. Why? Because it's an actual real number, right? And the imaginary part would be the number that's beside the imaginary number, which is root minus 1. So the imaginary part would be what? 3. Um, let's say it was this way instead. It was roots. Let's say you had 5 plus roots minus 4. What would be the real and what would be the imaginary part? So this would basically be 5 plus, remember again, root minus 1 times root 4. That would be 5 plus, let me just put this in brackets here, 5 plus 2i, right? And then remember, the imaginary part is this, since it's literally beside I, and the real part would be 5. Okay, so now that we have that cleared up, like I said, that's basically what complex numbers are about. I'm just trying to use this guide, by the way, just so we don't skip anything in the topic. We are currently somewhere here, basically just defining what a complex number is. And this is definition like I just showed you guys now. Okay, yes, we should be somewhere here. Perfect. All right. So before we go there though, now remember where I said I is equals to root minus 1. Now this is a very important um, equation. If I equals to root minus 1, remember imaginary number, root minus 1, imaginary, all the same thing. Now if I equals to root minus 1 though, we could actually find um, some indexes of I. So if I is equals to root minus 1, what will I square be? That's I times I. What will I cube be? Then what will I raised to the power 4 be? Very important things to find out. Remember, I square is just I times I from your indices. So what will I times I be? I times I would be root minus 1 times root minus 1, which in this case would be equals to minus 1. Like I said, you know this from your swords, right? If you have root a times root a, it's basically root a square, square cancel square root, and then you have a, right? And then I cube would be I times I times I. And remember, I times I is this. So we would have minus 1 times I and that would give us minus I. And then finally we have I times I times I times I. And then these two, we'll solve them here, right? So I times I is minus 1, and then I times I is also minus 1. So what would it be eventually? 1 or plus 1. So then it gives us the values for the indexes of I. Therefore, if I is root minus 1, I square would be minus 1. I cube would be minus I. Then I raised to the power 4 would be 1. So these are also really important things to note. And a complex number is one of those topics that build on other topics, right? It builds on trigonometry, you should know it. It builds on exponentials, you should know it. It builds on indexes or indices. So, and we'll see an example of that in some questions I would bring up now. So if we know that, and by the way, these are not things you have to cram. It's just things that you should know based on what we just did up here. So if we know what all this is, if we are asked to find I raised to power 8, for example. Now remember from your laws of indices states that one of the laws anyways states that um a raised to power xy is equals to ax all raised to power y, right? Which means if we are raising a number to a product of two numbers, we could just do them interchangeably. We could do one first, raise the number to one, and then raise the number to, or raise the value or the result to the second one. And let me just do a quick example if you're trying to wrap that around your brain. Let's say you have 2 raised to power 6, for example. 2 raised to power 6 is basically 2 times 2 times 2 times 2 in 6 places. But then, according to laws of indices, we could split this. Since 6 is a product of two numbers, 6 is basically 2 times 3, right? So 2 raised to power 6 would be 2 raised to power 2 times 3. And that would be 2 raised to power 2 all raised to power 3, which means take care of one of the numbers first, and then with the value you got, raise the value you got to the second um, number, right? So if we have I raised to power 8, that means we could just simplify that to be I raised to power 2 or raised to power 4, because it's the same thing, 2 and 4, right? 2 times 4 still gives 8. So we're still saying the same thing. And we could also use I raised to power. We could bring 4 inside first and then take 2 outside. Let me just rub this off. Sorry, guys, by the way, if my handwriting is throwing you off. I don't think I have very good handwriting here, especially. Okay, so we have I raised to power 4 raised to power 2, right? And then from math, any method you take would basically lead you to the same thing. If it doesn't, then there's something wrong. You should know that already. So let's try and solve this in any of these two ways and figure out if we'll arrive at the same thing. We should, but let's see. Um, so we could first take this one. This one is I square, then raised to power 4. Remember, I square is minus 1. Therefore, it's minus 1 all raised to power 4, which is what? Minus 1 times minus 1 times minus 1 times minus 1 in 4 places. I wouldn't like start showing how to do that, but the answer would be 1. And it will be a positive 1 because the power is positive, right? So the minus cancels minus, cancels minus, cancels minus, right? And then the answer is plus 1. Now, how about if we use this instead? From this, I raised to power 4 is 1. So which means we should have here 1 square. which is still equals to 1. So you'd get your answer either way. Any of the methods you use are perfectly fine. Okay, let's try something different. I raised to power 10. And by the way, you could try this. Let me give like a 30 seconds or so. Let's try this out, see if you'd get the same thing as me. You could just try it for 30 seconds, and if you don't get it, that's also fine. You can just watch after the next 20 seconds, you'll be able to see it. Okay, I raised to power 10. And remember, it doesn't matter which one comes first if you're able to divide it based on um what makes up the power, that's like solves 90% of the question. So if I raised to power 10 is what we are being asked to find, I raised to power 10 means I raised to power 2 times 5, right? And I raised to power 2, so this is what we're basically finding. I raised to power 2 all raised to power 5. I raised to power 2 is what? Minus 1. Therefore, we have minus 1 raised to power 5. And the answer would be minus 1. Okay, now in the questions we've done, the two questions we've done, we are basically checking scenarios where it's a straight product. What are scenarios where it's not a straight product? It's like a mixture of a product as well as an addition for the index. And an example of that is basically something like this. For example, could be like prime numbers. Prime numbers are an example of that because it doesn't have a straight factor, you know. So let's say I raised to power 7, for example. Find the simplified this, I raised to power 7. Now, if it doesn't have a straight factor, it gets a little scary or nothing to actually divide it from. But not really. You could still basically simplify this. How you could do that is just think of the nearest um the nearest number to 7 that has factors, right? Or that has factors that you like. So the nearest number to this is 6. 6 has a factor that is nice, 2 and 3, right? Apart from that, if you go back 5, 5 doesn't have anything, so you wouldn't use 5. 4, 4 is a good one, especially in this case since it still just goes to 1, right? 3 is a good one, 2 is a good one. So just depends on which one you'd like. So in this case, we could use 2, we could use 6, and we could use 4. If we're using 6, basically after figuring out which one is closest, just try to use your laws of indices to get back that same question. So that means instead of I raised to the power 7, we have I raised to the power 6 down, right? That means that's what we want there. And then the others could just go along with it, right? So if you have I raised to the power 6 down, and then what do we need to put here for this question to be the same? Because remember in mathematics, the left hand side must always equal the right hand side, otherwise something is wrong, right? So if you have I raised to the power 7, we have I raised to the power 6, we are choosing to use 6. It means we have to multiply with I. We have to say 6 plus 1 gives you 7, right? Which is the same thing as saying I raised to the power 6 times I. Because lots of indices, it still adds up to 7 either way. So let's just shelf this here. And then if you had to use 4, for example, let's say we have to use 4. If we had to use 4, we would have I raised to the power 7 is equals to I raised to the power 4 plus 3, right? And then that means we have I raised to the power 4 times 3. Times I raised to the power 3, I meant to say. So from what we just did previously, you could take care of this. And then whatever you get times I, that would be your answer. As well here, you could take care of this. And then you could also take care of this because this still has to be reduced. And then whatever you get, your answer will be there. So basically, if you get a question involving indexes of I, you should never leave it in any other thing apart from I or an actual number. If it's in anything else aside I or an actual number, then you've not reduced it enough. That means -2, -5, -6, -7, 0 works, I works, 2I, 3I, 5I, anything like that works. When you get a index of I as an answer, then that's not correct. It means you haven't reduced it enough. Right. Okay. So much of this will still be doing that in like later topics. So you could just stick around. We might not be able to cover like a lot. Like I said, it's a very huge topic, but let's see. Let's see how it goes. So after you figured out basically complex numbers, what there is to know about complex numbers, indexes of complex numbers, the next thing to do is addition and subtraction of complex numbers. Now, remember, from the initial thing we talked about was set of numbers, right? So we have set of numbers here. And remember, there are always rules in mathematics for every single thing you do. If you're adding integers, there's a rule behind it, even though you're not following a rule. You're basically just adding the numbers you have there. If you're having if you're adding rational numbers, numbers that have fractions in it, there's a rule. Denominator, get the equivalent numerator, and then right. So there's a rule to that, right? Now for complex numbers as well, there's also a rule for adding and subtracting complex numbers. And that rule stems from this x plus yj or yi. I promise to use I just keep interchanging between I and j. I'm sorry for that, guys. But yeah, it stems from this x plus yj, that rule I just talked about. So let's try to solve some questions on it here. All right. So we're trying to add and subtract complex numbers. Okay. Hmm. So how do you add numbers? 5 plus 4 equals to 9, right? What if you had 5 plus 4 plus 0.2? You could still add them all the same, right? Because it works. But in your head, what happens? You actually add the whole numbers first and then you add this one, right? So in your head, that's what you do. You separate both of them and then you add the numbers first, then you add the remaining or what's by the side. It's a bit similar for complex numbers. Complex numbers, you basically have 2 plus 3i, 5 plus 6i, minus 1 plus I, 0, minus 2 minus 3i, j. Um, so similarly, you just have numbers as well here. But then you see that from the previous notes that we have just up there, we said this is real number or the real component, and this is the imaginary component, right? So the same way in this your addition, you just basically in your mind add the whole numbers first, and then you figure out what the decimals are as well. For complex numbers, you add the like parts together. So like goes with like, and in imaginary number, that means imaginary part or component to be added with an imaginary component, and then real component to be added with real component. So let's say you're adding these two, for example, 2 plus 3i, 5 plus 6i. Now remember, the real part to be added together, that's 2 plus 5, right? That would be 7. And then the imaginary components will be added together. That would be 3 plus 6i, which would be 9i. Do you see that? So it's just like a regular addition. 2 plus 5, 7. 2 plus 6, 9. Don't ever add them together. Ever, ever, ever. Nope, it's a crime. You should be punished. You should be jailed. Yeah, I mean, you guys wouldn't be jailed, but please don't do it. Don't add them together. It's a crime against humanity. No, I wouldn't stand for that. But yeah, like you could clearly see this is a separate number from this. If it could be added together, it would have been added together right from here, right? But it wasn't. It's two different numbers. 2 plus 3i. It's a real component and an imaginary component. So when you are adding them together, add the real component together and add the imaginary component together. Always, 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 always. Right? So let's say we're adding this instead. We're adding 5 plus 6i minus 2 minus 3. This is j. Let me just change this to an I. Like I said, guys, it's a really interchangeable. The difference is based on where you live. Okay, yeah, and it's confusing for me because I grew up using I, and then based on in my recent studies, I'm now using J. So I'm trying to figure out. It's hard to keep up, but really they all mean the same thing. So yes, here you have 5 plus 6i, then you have minus 2 minus 3i, and you're adding, still adding, right? So what do you do? Add the real components together. Now in adding the real components, it will be 5 plus minus 2, or 5 minus 2, which will be what? 3. You guessed correctly. And then the imaginary component, that's 6 plus minus 3, or 6 minus 3, which would be plus 3. So that would be, um, let me do. Yep, that would be 3 plus 3i. 3 plus 3i, and that's what you get when you are trying to add them together. Now, um, there are a couple more like practice you could do on this. We could probably try here. Since it's a yes, so it gives us some questions right from there that way. You could try it out. See what you guys think the answer would be. Here we have 2 plus 3i, then 2 minus 3i. Z1 is 2 plus 3i. And then Z2 would be 2 minus 3i. Find Z1 plus Z2, and then Z1 minus Z2. Okay, so in this case, remember always real parts together, imaginary parts together. Doesn't matter what the question is, doesn't matter anything that's going on in your life, any issues you may have, it's always real parts together, imaginary parts together. Always, always, always. Okay, so in this case now, the real parts together would be 2 plus 2. You could use brackets maybe if that helps you see it better, right? And then the imaginary parts together, you could just use the I here, then open the bracket and figure out what's there, right? That would be 3 minus 3. 2 plus 2 would be 4. 3 minus 3 is 0 times I, still 0. So Z1 plus Z2 would be 4. How about Z1 minus Z2? 2 minus 2, because it's 2 minus 2, right? Like I said, you could group it, then figure out and do for I. Now I is 3, the first one, minus minus 3. That's minus minus 3, right? And then 2 minus 2, we know that as 0. And then plus I times 3 minus minus 3 is 6. You should know that. And the answer would be 6i. So Um, this is coincidental, by the way, um, due to the fact that these two are called conjugates. In a later video, I'll explain to you guys what that means. But you see how in this case, in every case, no matter what the question says, we always added real part together and the imaginary part together, even if it was subtract, if it was a real, or if it was addition. But with this only, this method is for addition and subtraction. There are many other topics to cover in complex numbers, many other things to know about in terms of multiplication, indexes, various other things. But for this, or for now, addition and subtraction, you guys should be golden with this. Now, we've kind of finished the hands-on practice and for complex numbers. There are always my resources online. You guys can always check them out, see how they could help you solve some questions. You should be good to go. And the second part, which is one of my favorite things about complex numbers, especially in exams, is the fact that your calculator could actually do all this for you. The calculator is really good with that. If you have a natural display, which is one of my favorite calculators, natural display has that. If you're from Nigeria, if you have a wire calculator, I don't think a wire calculator should not have that. But if you get just a regular Casio, Casio should have that. Yes. So basically, what am I talking about? Now, a calculator actually has a mode called complex, where you could, mm, how do I put it? Basically, make calculations within complex numbers. And it has a mode right there. Not many people know about it, and not many people know how to use it. So I will show you guys how to use it now. Remember, we are just in addition and subtraction. So I'll just show you guys how to use all everything we've learned today. So by the way, this is what my calculator looks like. It's a natural display, it's just regular, nothing too fancy. You might have one that's like curved somewhere at the bottom here. It's still the same thing, really. It's still a natural display. You could do everything this can do. So what do you do now? First of all, look on the buttons on your calculator, the number buttons: 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Look at those numbers. Do you see something written above them? Like it should say vector, matrix, CONV, CONST. You might not have those two. But you should have vector, you should have matrix as matrix, you should have stats or something like frequency, you should have table, and you should have CMPLX. Now that stands for complex. That stands for complex. And that's basically the mode you would want to be in when we are working in complex numbers. Now to go to that mode though, you have to use the literal mode button. So just click on the mode button. It should say comp CMPLX. Click on that CMPLX. That's number two in my case. It should be also number two if you're using a natural display. But now you are in the complex mode. How you know that is at the top. I'm not sure if you guys, yeah, you guys could see it. At the top, you should see CMPLX. Perfect. If you have that, that's the first step. Second step, um, you should try to figure out where your I button is. Your I button. I wouldn't know where exactly it might be for a Casio to check that out, but for natural display, it's usually above the button that says ENG. Do you see that there? It's above the ENG button. Oh shit. Yeah, there's an I right there. Yes. Good. So you should locate that on your calculator. Now the I basically stands for imaginary number. Now how can we actually do this? Additions, common additions, you could do this on your calculator. If you had started from the last question we just did, 2 plus 3i, you type it 2 plus 3i with the I literally there, plus 2 minus 3i. You would also type it out. your answer would be 4, which is what we just did. You could try to subtract. The answer should be 6i, which is what we just got. You could try various other things like what we mentioned up here. Or we mentioned what we did up here with indexes. You could try that, for example. You could try I raised about 2. It's going to give you -1. You could play around with that mode. Just try to figure out some of the other things it does and try to familiarize yourself with it. One of the best ways to gain mastery of your calculator is by actually using it. You have to actually use it and figure out the tricks and crannies of the calculator. So yeah, that's pretty much the basics of complex numbers. We covered what complex numbers actually mean. We covered addition and subtraction, and we covered indexes of the imaginary number. So in another video, I will talk about some other topics like other forms of complex numbers, how to actually represent this, and yeah, we'll see how it goes from there. Like I said, it's Kingsley, and it was nice making this video. I've been trying to make this for a long time, just been postponing it. Let me know if you like this video, and I can keep making more. Bye now.